be returning it too.
Wednesday.
This is lectures.
We're not going to talk about that.
Based on what he's so far.
We're not going to talk about
Yeah.
that.
I think I can do like the first 1.5.
No.
You-
And they're happy by their total. So that means
Except there's no Sunday.
some days.
It goes back. But what do you think today? No, this is next Friday.
Yeah, but today's lecture is the last lecture that the homework will cover.
I think if you look at it,
There's no new notes yet. Okay. All right, good afternoon. On a nice spring day. Actually, it turns out that I barely made it. I actually got struck by snow in Dallas last night. Can you imagine being spring here and snow in Dallas? So the world is going upside down. But hey, I got out in time and made it just in time for the lecture. Good. So a couple of things I would like to discuss and talk about. Next Wednesday, I would like to go to a couple of things. By then, we should have graded the midterm. So I would like to spend some time on the first midterm on Wednesday. And we're also going to talk about the project. So that's make sure it's an important lecture. We want to go through what we were after in the midterm and how things went. And as I said, we're going to introduce the project as well. And we should start running it. I think you should be able to start flowing and running on the project by the end of the week, next week. Okay. What else is there? There's no labs for a while anymore. I think we're basically done with the labs. It's now project phase. We have one more lab left, which is going to be a hardware lab. We're going to kind of figure out exactly when to do that. But I think it's important that you get more into the project cycle first. I'm going to also, we need another homework. That's probably going to be posted by Monday. So we're going to need another homework, which I'll give you about 10 days for. It's a fairly elaborate one, so I'll give you 10 days for that one. Okay? So that's the practical side of the things. Any questions? Issues? So I think from my skill perspective, I think I still have, from a travel perspective, this last Wednesday was the last lecture I missed. So from now on, as far as I look and nothing emergent and nothing weird happens, I should be able to make every lecture from now on the right. So that's the good news. All right, so let's talk about the logical effort. That's what I'm going to talk about today. So what you saw last class is the fact that if you think about CMOS gates, NAND gates, NOR gates, and things like that, you see actually while the inverter is a very good component, from the time you start increasing the fan-in, you start seeing some challenges, right? You start building fairly elaborate RC networks. And I'll briefly repeat this right now, but one of those properties of an RC network that the delay of a more complex RC network doesn't go up linearly with the fan-in, but it goes up more like quadratically, right? So if I have a fan-in, if an inverter has a fan-in of 1, if I basically double the inputs, well, it's kind of hard to say. If you go from fan-in of 2 to fan-in of 4, your delay goes up quadratically. Let's say from factor 2 to 16, or 4 to 16 approximately, 2 to the squared, 4 to the squared. Which means that large fan-in gates are very expensive from a performance perspective. And obviously there's certain things we can do about it. And that's what the end of last lecture was. There's some optimizations I can play to get around that. And that's obviously going to be very important because, as I mentioned before, the majority of the CMOS structures we implement are all implementing complementary CMOS. So trying to do something to get better performance out of these guys is a good idea. And there's a couple of tricks you can play. But if you really want to go faster than that, then you have to do something different than complementary CMOS. And that's why there's other logic families, like pass transistors, or like dynamic logic to go faster. But let's first kind of look again at traditional complementary CMOS. What can we do in optimization? And then even better, can I do this in a more informed fashion? Right? At the end of the last class, you saw a bunch of tricks. Right? I call them tricks. Things you know, rules of thumb. So, okay, you kind of look from this. This looks like a good idea. Let's do that. But how do you know it's good? How do you know what the best thing is? That would be nice, isn't it? Right? I take a design, I can say, hey, that's the way you should size it. That's the way you should divide it over different gates, and I can do this automatically. That's really neat. And I can say, you're not going to beat me. This is the best possible design with this particular technology. So that's really what we're going to talk about today. Is there a way to express the delay of our gates in such a way that we can automate part of the process? We can put something in MATLAB. I can write down a set of equations. I take some derivatives and say, hey, this is the best. And this is an expansion to what we did before for inverters. Remember the cascade of inverters? Where we found a set of tricks. We wrote down a nice analytical, or not tricks, we wrote down a nice analytical equation and said, okay, with this equation I can prove that this sizing, remember 3.67 or something like that, that's the best thing you can do. Nothing is better. We would like to do that for more complex logic networks as well. So, but before we do so, let's briefly go to some of those techniques that you discussed last class, just as a little recap. Okay? So I think Simone went through this in the lecture and in the discussion session, but let me just briefly repeat this. If you look at a pull-down network of a NMOS gate, can I switch to the overhead projector, please? Doesn't.
Other side.
What's it?
It was showing up on the other side.
Oh, the other side?
No.
Okay. No, that's me. Okay, there we go. Good. So you look at a network, pull-down network like this. Like suppose I have a 4 fan-in type of a pull-down network of an AND gate. That's really what you get, right? You have a chain of capacitors and resistors. Before we say, well, what you could do is lump all those capacitors into one, and I lump all my resistors into one. That's something I could do, right? You can say, okay, this might become a capacitor. Let's say these are all the same. You can say this is 4C, and this is 4R, right? That's one way. Lump all the capacitors together and lump all the resistance, and then I would get a propagation delay, which is 16 times RC, which is this quadratic relationship we talked about. In reality, this is not completely correct. Remember, if you have a network like this, so in reality what we have here is a network where we charge or discharge a capacitor. Let's look at the charging part for a second here. Looks like this. It's a lot of drawing work. But you look like something like this. Suppose I want to charge up this node. I want to put a step here, or I want to put a step down. One of the two. Step up or step down. I can do both cases. It doesn't matter. It's symmetrical. Remember what I could do is basically say, oh, gee, I can write down the differential equations of this. Right? That's one thing I can do. I solve it. I look for the complex differential equation, and I look at the 50% transition point. And I try to solve for that. Very complex, very painful. In a couple of lectures from now, we're actually going to show there's an easier way to at least find the 50% point, the time constant of this network. Call it the dominant time constant of this network. That's really what we care about. The one that's going to dominate the time domain response. I'm not going to go into a full lot of detail here at this point, but we'll come back to that later when I do wires. But it's kind of interesting to understand what's going on here. So let's assume that they're all the same. What we can say is that the dominant time constant, so the prime constant, we'll have a set of time constants in a network like that, right? You will have 4 probably. But the dominant one, that really is the term, you can find by actually saying, well, actually I have one capacitor to measure, this one doesn't matter, is that you take the first resistor, right? You look at this chain. This is a chain of resistors and capacitors. And you look at the first resistor, it says, how much capacitance does this resistor drive? Well, it's 1, 2, 3, 4. All the current to charge this capacitance set has to go to these resistors, right? So we have a first factor, which is R times 4C. Okay? So you look in the chain and say, here's a resistor, and what's the total capacitance that basically hangs off to that? Okay? That's the first factor, but there's some more factors, right? Because the other resistors will contribute to the time constant as well, but not as much. Because you look at the second resistor, the current, the charge, it only has to carry the current, the charge to charge up these 3 capacitors, not 4. But if you look at the charge up, there's going to be a current go to this resistor, which basically charges up these 3 capacitors. So we have a second factor, which is R times 3C. Same thing with the third resistor that only charges 2 capacitors. And the last one becomes RC. And we can say that this, if you look at this actually fairly closely approximates the time constant we're interested in and gives us a first shot at the propagation delay. Okay? So this is a way of approximating the delay of an RC network. Again, it's a first feeler. We're going to talk more about this later when we talk about wires. Because wires are whole networks with lots of resistors and capacitors. So we're going to talk more about that at the time. And I'm going to do some more sophisticated things. But the reason I wanted to show this is that there's some very simple conclusions I can draw from this. Right? If I look at this equation, it says, hey, if I would do the sizing of my transistors, Okay, I size them up, size them down. What should I do? Should I make all transistors equal? Right? I can say if I size up a resistor or size down a resistor, I make my transistor wider, I'm going to increase my capacitors, right? But should I do this equally for all transistors, or should I make them different? Should I size my transistors in a different way? So what do you think? If you look at this equation tells you a lot, right? So let me make this a little bit more explicit. Actually, this is equal to R1. If I now put numbers here, and I make them different, this is C2, C3, C4, what we get is we get R1 times C1 plus C2 plus C3 plus C4 plus R2 times C2 plus C3 plus C4 plus R3 times C3 plus C4 plus R4 times C4. Right? That's when I make them different. I have different capacitors here now. So the question is, what should I do? Should I make them all equal? Or should I differentiate between them? And if I would differentiate them, how would I do it? Any thoughts? Just looking at this equation. What is the most important resistor in this network? Yes? 4? Resistor? R4. Why would you think R4? Suppose I have this thing here, right? What's the biggest factor? He basically got very nice. It's R1. Very good. That's what I call the perfect setup. Anyhow, yeah, you're right, R1, right? Because R1 has to charge up all those 4 capacitors. If I make R1 smaller, I'm going to gain more than making R4 smaller, right? So it's clear what you would like to do in a network like this is to gradually decrease, or if you look from the back here, you would like to gradually increase the size of the transistors depending upon where the charge is basically being stored. So let's get back to the computer now. Again, you look at this NMOS network, you see here you have your pull-down network, the same network, right? There's a bunch of resistors and capacitors. What is the most important transistor in this particular case? Well, if I have to discharge, this transistor here, M1, only discharges C1. So it can be made fairly small. And then I can make M2 a little bit larger, M3 larger, Mn should be the largest transistor. And that's really what's going to minimize the delay of this particular network. We call this progressive sizing. Yes, yes, thank you. Yeah, M1, sure. M1 charges all the capacitors, M2 has less, Mn does only one capacitor. Sure, thank you. So this is called progressive sizing. Now, you do this well, it actually can have quite a bit of an impact on your performance. Actually, your delay can go down quite nicely. But you have to be a little bit careful, because you might get carried away with this. So, oh, wow, cool, right? And I take my transistor, I'm going to make them all different, and it's really nice. Till you finally have to go to layout. Now, how would I lay out this type of thing? Well, I have a number of inputs here, which are, so I have, let's say, my different polysilicon strips. Normally, with a NAND gate, if you typically an NAND gate, the way I would implement, I put a piece of diffusion down and then put strips of polysilicon over them. Right? Bingo, 3 transistors in series. And the nice thing about this thing is that the diffusion regions between those, oops, did I mark the wrong one? No, this is right. The diffusion region between those are actually very small, because there's no contacts whatsoever. It's a diffusion strip, and you go from one transistor to the next one, to the next one, to the next one. No contact, really small capacitance. Now, if I now start gradually sizing my transistors, what I would have to do is the following thing, right? So here's my diffusion. The bottom transistor has to be the biggest one, so I start with a big transistor here. Now, if I now want to go to a transistor which is a little bit narrower, I have to somewhere put a jag in there, in the layout. So I have to do something like this, right? This is one way of making my transistor gradually smaller. However, there's some darn design rules which say that the edge of your diffusion here has to be a certain distance away from your polysilicon. So what this forces me to do is push the polysilicon further away from each other, the polysilicon line, which means that the diffusion capacitance goes up. And as a result, you get some extra capacitance in there, which slows you down. So it is not as simple as say, easily, bingo, 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 we're done. Now you have to take the layout into account in this particular case. And some of the gains that you might win at the spice level might be lost once I go to a layout level. Be very careful with this type of things. But this is a successful technique and actually been used very successfully, for instance, in decoders of memories, where you have very large arrays and the wires are pushed aside anyhow, so you have the space to do this jagging. So that's fine. So but be aware of that. So that's trick number one. Trick number two is also a very important one. If I have a complex network, let's say I have a complex network here like this, NAND gates. Okay, so these are my primary inputs. Assume that all my inputs here, the 4 inputs, arrive at the same time. Okay? They all change exactly at the same time, or they arrive at the same time, as we call it. Okay? This path here is what we call the critical path, because you can see this input here only has to traverse to one gate. So the path from this input to the output is one propagation delay. This input has to traverse to 2. So it's clear that the delay of this thing is not going to be determined by this guy or by this guy, but the input's coming in here and traversing all the way to the output. So it's what we call the critical path, or the longest path through the logic. Okay? So now let's look at this gate, for instance, this NAND gate. This input, the bottom input, let's call this input number 1. Assume that everything, well, let's do it a little bit different. This is 1, 2, 3, and 4. Okay? 1 and 2 and 3 and 4 basically all change at the same time, right? That's what we assume. Now, if you look at this gate number 2 here, the second gate, we see that the input to that gate, number 3, input 3 will arrive instantaneously. Right? It's there, bingo, changes. Input X, however, is going to arrive a little bit later. So you want to make sure that input X, when it arrives, goes to the output as soon as possible, because it's the critical one. Okay? So you can see that if I have a complex network like this, you have, let's say, 3 inputs. Okay? In 1, in 2, in 3. These are my 3 important inputs. Some of them might arrive earlier than other ones. The ones on the critical path, obviously, are the ones that are going to arrive the latest. And I want to make sure that they're basically going to propagate the fastest. So we can play some games here, because I have some choices, right? From a transistor perspective, it doesn't really matter where I connect in 1, in 2, or in 3. I can connect into any transistor, right? But in reality, it matters. Because, for instance, if you look at this case here, suppose that in 1 is the critical signal. Okay? Thank you. The notes just got in here. Good. So you can pass them around. That would be great. Thank you. So if in 1 is the one that arrives the latest, okay, then you can see that in 3 is already set. Let's say this is already 1, this is 1, but capacitance C1, C2, and CL are still charged because transistor M1 is still off. So the critical signal arrives. What I have to do is discharge all this capacitance in one shot, which is going to be slow. Okay? Let's now look at the reverse case, where I put the critical signal on the top. Okay? So a little bit before that, in 2 and in 3 arrive and basically start happening. What they start to do is already pull those nodes down. So these intermediate nodes will be already at 0. The output node will still be high, but the intermediate nodes will all be pre-discharged. And then the critical signal arrives. The only thing I still have to do is discharge CL. So you can imagine that this is going to be faster than putting the thing on the bottom, where you have to discharge all the capacitors. So basic rule here is the transistor, which is connected to the critical path, should always be as close as possible to the output. Right? Like in this case, transistor N1 is the one on the critical path here. That's the one which should be as close as possible to the output. So you can play some games with the ordering of the inputs. Okay? That's trick number 2. And actually, automatic tools like Synopsys, when they do the automatic mapping, will do this perfectly. They're really going to look at all the possible orderings, and they pick the right one for you in such a way that minimizes delay. So tools can do this automatically. Okay. Here's some other options. You look at the same logic function. 3 different implementations. If I look at it, it's kind of fairly hard. I would ask you, all of those do exactly the same thing. Now I can ask you, which one will be the fastest? Right? It's hard to say. It's not obvious, at least not to me. Maybe to you, but not to me. Because I don't know. I don't know the numbers, how they relatively compare. But it's clear there's going to be some difference. Here, remember the quadratic dependency? Right? So this thing here has 8 inputs. This is going to be a very slow gate. So what we did in this case is decompose it into 2 4-input gates and 1 2-input gate. So the disadvantage is that I now have 2 gates in sequence. But the nice thing is that those big gates now, or the 4-input gates, are going to be quadratically faster, a factor 4 times faster than these other really big gate here. I probably can think that this is going to be better than this. So I would pick this one. Now the next thing is, can I go to 2-input gates instead? Instead of 4-input, I really decompose it again. Now I have 4 layers of logic. Will this be faster than your own? I don't know. It's hard to say, because now I get 4 layers, and the difference between a 4-input gate and a 2-input gate might not be this big. So it would really be cool if I have a mathematical tool to be able to compare the two and say, hey, I can tell you this is better than that. And that's really what logical effort will allow us to do so. I'll give you an answer to this question in about half an hour. Can you tell you exactly which one is going to be better than the other one? Okay? Okay. This is another example of logic restructuring. Suppose that in1 is the critical signal here. And somebody has designed for you this logical network. Doesn't seem to be too clever to me. Right? If you look at all your inputs in 1, in 2, in 3, in 4, in 5, they all arrive at the same time. But even if only in 1 is critical, putting the critical signal on the longest path seems to be the dumbest thing to do. Right? Because it's already critical, it's the one that arrives the latest, and then you're still going to make it traverse to a long thing. So what I would do in this case is say, well, gee, I'm going to reshuffle this network a little bit. Just using Boolean transformations. It's not hard, right? If you look at the logic function this thing implements, this is a NOR gate. So this is equal to in1 invert plus in2. That's the NOR gate function. And then this is an AND function. So we get this, and in 3, and in 4, and in 5. All right, that's the logic function this thing implements. That's out. Okay? Now I can easily rewrite this. This can become equal to in1 time and in 2 invert, and in 3, in 4, in 5. And what I should do is now isolate in1 in such a way that in1 is then sitting in the last stage. I'm going to take all those guys together, let's say, and now make an AND function. Let's make an AND function with an invert, and an AND with an invert as an AND. And I'm going to put in1 here, and then I put a logic network in front of this, which implements the other stuff. This, the rest of this equation here, that goes in here. But now the advantage, you can see that in1 only has to go to this last stage. And that's a lot better, because you want to make sure that the critical signals see the shortest critical path. This is just logical restructuring. Okay? So there's many ways of doing that. But it's playing around with Boolean expressions. Reducing the swing, I think that Simone discussed that. Sometimes it's better to have a logic swing which is smaller. We'll come back to that later. Let me just jump over that for the time being. And then here's another important one. This is it's something that, once again, makes logic sense when you think about it, but very often is forgotten about. It's really a divide and conquer approach. If you try to do too many things in one shot, very often you're going to fail, right? Very often, that's in life as well. Very often you say, well, I really have a very complex thing to do. Let's separate them out and do each of them in the optimal way and then combine them together. Here's an example. I have a complex logic gate, which is slow, and suppose I have a very big load capacitance, right? So I have a very complex gate driving a very big load capacitance. Now we know that complex gates are not very good in driving large load capacitances, because we're going to have to discharge, let's say if this is an AND gate, we have to discharge this big capacitor to this chain of transistors. Right? An inverter does a much better job at driving capacitor. There's only one transistor in the up or down link. So what I could say is, well, gee, if in order to deal with those type of things, I could make all my transistors bigger. Right? I can make this thing huge. But that's expensive because I have so many transistors in this thing that I have to make them all huge if I want to be fast. That's very expensive from an area perspective. So let's separate out the tasks. Let's divide them. And say, okay, I have to drive a big capacitor. Oops. What's the best thing to do that is just use an inverter and size it appropriately to drive that capacitor. Okay? And then I'm going to have maybe, let's call it an AND gate for the time being. It's a little bit simplified. Let's call it an AND gate. I'm going to take this AND gate driving this inverter. This I can optimize for the delay. I can size the transistor very carefully to minimize delay of this complex logic network. With a kind of small load capacitance in here, I don't have to worry about load capacitance. This inverter I can optimize to drive the big capacitor at the output. So you'd separate the problem of a large complex logic network and a large capacitor. We call this buffer insertion. Very often it's a good idea to just insert a buffer between a big capacitor and a complex logic network, because it helps you to optimize things in a much better way. Okay? But again, how do you know? You trust me right now that and it makes logic sense, but how many stages should I put in there? Should I put 4 inverter stages? 17? 1? Or maybe none? If you don't have a mathematical tool in your hands to play around with it, you're toast. Right? It's just this. Or it's optimization through SPICE. I see this very often too. Right? Somebody says, okay, I have to design an op network. I do my SPICE run, and I run it and say, okay, I get a number. No, let's change the transistors. Oh, this is faster. That's cool. Let's make them bigger again. Oh, it's even better. It's even faster. And you run about 1,000 SPICE runs. About 3 days later, you come up with an answer, which might be still wrong because you might have forgotten some. So this optimization through SPICEation is a really bad idea. And I see it very often happening. It's in industry, people run these massive SPICE runs without thinking about the problem. Very often it's just, let's sit back a little bit. Think about the problem. Get a nice little mathematical formulation that puts you in the right position, and then run SPICE to figure out if it's exact. Right? SPICE is a beautiful tool, but don't misuse it. Use your brain occasionally. It helps. Okay? Good. So let's give you the tools in hand to make it happen. That's what this logical effort is all about. And that's what we're going to talk about next. Okay. Remember my buffer example. It says, gee, I have a large capacitor to drive, and I have an input capacitance somewhere given because of the fact that I don't want to load the previous stage. Question was how to optimize the number of stages and how to optimize the sizes of those inverters. And what we did is say, well, gee, I can write down the propagation delay as a function which is approximately like this. It says T invert times the sum of some gamma, and gamma is the ratio of the diffusion capacitance and the gate capacitance of the gate, remember? And a factor F, which is the fan out. And the fan out is the ratio of the gate capacitance of your gate and the load capacitance, the external load capacitance. That's the fan out. I look at this gate here and I see how much capacitance do I see in here and how much capacitance does the next stage present to me. Okay? Very simple equation, but very nice because I can express the total propagation delay, start taking derivatives of it, set the derivatives to 0, and we came up with some nice answers. Nice answer, one of two things to remember. The optimal design of this thing is the design that basically will make the delay of every stage equal. So you're going to divide the load or the effort equally over every stage. Okay? So the fan out F factor is constant for every stage in a network. That was the first conclusion. And the second conclusion was, how many gates should I put in between? Well, we came to the conclusion that something basically that created a fan out factor of 4, say setting Fi approximately equal to 4, was about right. It's a good number most of the time. Okay? So that's good. That's an interesting result, but obviously works only for chains of inverters, which are only useful for buffers or drivers. I would like to use the same technique now for complex logic networks. And that's logical effort. So let's look at a slightly more complicated network. Not much, but slightly more complicated. I'm going to use an AND gate in here now, an inverter, and a NOR gate. So I have 3 gates. I have some input capacitance here. I have some output capacitance. And I would like to figure out how should I size those gates. It's an AND gate, an inverter, is an NOR gate, in such a way that the delay is minimized. That's the question I'm really after. Okay? Well, as before, we have our equation. What you can do is just write down, using what we already know, I can write down the delay expressions for the NAND gate. Okay? Let's look, for instance, at the pull-down network, which is going to be the critical one for a NAND gate. Right? The pull-down is when you have 2 resistors in sequence. Right? So we see that the resistance of this network, if I don't size anything, right? So okay, the resistance of this network is 2 times R, the basic resistance of a device, divided by W. Okay? And the capacitance is going to be the load capacitance plus the diffusion cap. And for the diffusion cap here, we're going to assume that I have one capacitance, which is coming from this transistor, and you have your PMOSes adding 2 more capacitors. So I get about the capacitance which is equal to 3 WNJ, approximately. Okay? The input capacitance that I see from the NMOS network is 2 times CG. Right? I see basically 2 equal things. So I can plug in the numbers. Doesn't matter what exactly the numbers are. I'll come back to that. Don't worry too much about those 3s and 2s. But the bottom line is that I get an expression again, which is of the same style as before. Okay? I have somewhere a delay expression, which is, let's call it T NAND, an intrinsic relation. A factor which is a function of the fan out, F. And a fraction which we call gamma NAND now for the time being. Gamma NAND being a part of a function of gamma, and another factor which is 3/2. Again, don't worry about the 3/2 right now. I'll show you exactly how we're going to derive those things. Okay? Similar to the previous equation, but you can see that some parameters have changed a bit. Especially this one and this one. Okay? So what I'm going to do now is take my basic delay expression and I'm going to modify it a bit. Just a bit. That basically captures this result. And by the way, I can do this for the NOR gate as well. I can go to the NOR gate, looks at the input, look at the load capacitances and all this type of things, and I write down an expression. And again, this is F, this is gamma NOR, this is T NOR. Okay? Cool stuff, but not very useful yet. So what I'm going to do next is this. I can add the whole delay together. That's one thing I can do. Say the total delay of this network is the delay of the gate, first gate, the NAND gate, plus the delay of the inverter, plus the delay of the NOR gate. Right? Just taking the three expressions, putting them together, and I get my total propagation delay. Now, it's kind of hard to figure out what the relationship between some of those factors is, so I'm going to play another little transformation. I'm going to normalize everything to the intrinsic delay of an inverter. Remember, the intrinsic delay of the inverter is the inverter delay without the load. So I'm going to divide everything by T invert. So I get here T NAND over T invert over T invert, that's 1, T NOR over T invert. So it's kind of a simple, nice little game. From now on, we're going to look at delay, not anymore as nanoseconds, but how many times is it larger than the intrinsic delay of a inverter? 10 times, 7 times, 4 times, things like that. Okay? So, here's now my new equations. It says that the delay of any gate is equal to this factor. That's, remember, the NAND gate and NOR gate is pretty similar, right? So you have a K times T invert, right? So you have T NAND, so let's divide the factor K. Gamma G, which is the gamma of that particular gate, plus the fan-out factor F. Okay? Nice, but I still have this K sitting outside here. I really would like to express everything as a function of T invert. So what I'm going to do is divide this whole thing by K. Okay, I move actually K to the inside. Okay? So I get here now the delay is going to be T invert times K times gamma G plus K times CL over Cn. Again, exactly how this works out doesn't matter. The only thing that really matters is the expression at the end here. What I'm saying is that the delay of any gate, NAND gate, NOR gate, and/or inverter, whatever complex gate you have, can be expressed as a product of two factors. First of all, it's a product times T invert. Then we have a factor P. P I call the parasitic or intrinsic delay again. Remember the intrinsic delay? That's the delay of the inverter or of the gate without a load. So for an inverter, P typically is 1. The intrinsic delay is going to be T invert. Okay? If you have a NAND gate or a NOR gate, you can imagine that the intrinsic delay of a NAND gate, it's a more complex network, is going to be larger than if you have no load on a NAND gate or a NOR gate. You're going to have a delay which is larger than what an inverter would give you, intrinsically. You can imagine, right, that it's very hard for me if I fix the input capacitance. Say you have to have the same input capacitance. A NAND gate is always going to be slower than an inverter. So that's this P factor. How much is it slower? Without taking into account the load factor. And then we have this interesting product here. Product of two factors. Factor F is the fan-out factor. And fan-out is, as we have defined it before, is the input capacitance of the gate, looking into it, and the load capacitance, the ratio of those two. How much impedance transformation am I doing with this particular gate? But interestingly enough, there's another factor here, which is this LE, which stands for logical effort. Logical effort, it's an effort, right? In order to drive a capacitor, I have to work. How hard do I have to work? Well, think about it again. If I have a capacitor and I drive it with an inverter, sorry. Okay. And I fix the input capacitance here. So you have to assume that the input capacitance here is fixed. You can imagine that an inverter is going to be better in driving that capacitor than a NAND gate. Suppose now a NAND gate which has the same input capacitance. It means minimum size devices. You will have you're going to be having a much harder time to drive that capacitor to this NAND gate, because remember, when you do the pull-down network, I have two resistors in series. And I'm not allowed to size them up because I fixed the input capacitance. If I would make my resistance smaller by doubling the transistor sizes, I also double the input capacitance, which I'm not allowed to do. So for the same input capacitance, a NAND gate has to work harder to drive a capacitor than an inverter. Okay? And that's true for a NOR gate as well. And it's true for any other big gate. So that ratio of how much harder do I have to work is called the logical effort. Right? So 3 important factors here. So we have T invert, or 4. T invert is the intrinsic delay of an inverter. The delay of an inverter without the fan-out, without the load. P is the parasitic delay of the gate. The gate without the load. So for an inverter, that's 1, obviously. For an AND gate, NOR gate, and so on and so forth, P is going to be larger than that. Because network, even if I don't have a load, the delay of that NAND gate is going to be larger than the delay of an inverter. So the parasitic delay is going to go up. And then you have this factor which is the product of the electrical effort, which is the effective fan-out, and LE, the logical effort. And as I said, for an inverter, there's 2 things that hold. The logical effort is 1. We always normalize with respect to inverter. Right? So obviously we would expect that an AND gate will have a larger logical effort, or NOR gate. And the same thing, the parasitic delay of an inverter is also set to 1. Or to gamma, it depends on how you play gamma. There's little games you can play. Don't worry too much about the gamma thing. Okay? So, cool. So from now on, I'm going to say, forget about this T invert. That's a normalizing factor. Remember I said I'm going to normalize everything with T invert. And from now on, say when I say delay is 7, I mean basically 7 T inverts. So the delay of a gate now is described as P plus E times EF, or the effective fan-out, where the effective fan-out is not only a function of the electrical fan-out, but it's actually the electrical fan-out multiplied with this logical effort, which makes my load seem a lot bigger than it would be if I would drive it with an inverter. Okay? So we basically retain the same equations as we did before, but I just added some parameters to it. P, L, E. That's really what I added to the game. F remains the same, that we had that before. So I just added this parasitic delay, or intrinsic delay, and the logical effort equation. Now, important thing is that the logical effort of a gate is independent upon the sizing of the transistors. It's something which is purely a function of the topology of the gate. So I make everything bigger or smaller, doesn't matter. LE is a constant. So actually what I could do is I have a certain technology, I implement all my gates. For every gate in my library, I can compute the logical effort in advance and store them in a table. I know them, bingo, we're done. So this is not something I have to keep on doing every time. It's purely a function of your library and the structure of the gate you're building. Okay? The effective fan-out, though, is a function of the load and the gate size. The effective fan-out is a product of this logical effort and the electrical fan-out. So let's think about the logical effort and see if we can compute it. Okay? So, as I already mentioned, the inverter has the smallest logical effort. Because it's a very simple network, it's really good at driving large capacitance. And has also the smallest intrinsic delay of all static gates. I would expect. Anything else is going to be slow. Okay. So how do you define the logical effort? There's 2 ways of looking at it. Right? If the logical effort, suppose I approach number 1. It says I'm going to assume that the input capacitance of my inverter, I have an inverter driving capacitor, or I have a NAND gate or a NOR gate or more complex gate. I'm going to assume that the input capacitance remain constant. So I'm going to normalize it with the input capacitance. Now, in order to get the same delay between the inverter case, so we have the inverter here driving this capacitance, and I have my complex NAND gate. Okay? Something like this. Right. So I want to size the gate to deliver the same current as an inverter. So this current basically provides certain things. So if I want to basically get the same propagation delay, right, what I will have to do is make all my transistors bigger. Right? For instance, if you look at the NAND gate, I have to take the 2 NMOSes and make them double. If I double them, I will have the same resistance as the inverter has. But while doing so, I double also the input capacitance. So the logical effort can now be measured as the input capacitance of the inverter over the input capacitance of this complex gate. That's the ratio. For the same current, the more complex gate will have a much larger input capacitance than the inverter case. That's one way of looking at it. The other way of looking at it is, if I fix the input capacitance of both cases, how much slower is the complex gate going to be compared to the inverter to drive the same capacitance? It's the same thing, right? It's exactly the same thing. There's two ways of looking at it. I typically prefer to pick this one here. Okay? Size the gate to deliver the same input current as the inverter, and then take the ratio of the gate input capacitance to the inverter capacitance. Okay? And that's what we define the logical effort. Okay, so let's do some exercises. Let's try to do this for some real cases. Okay, here we are. Let's start. That's an inverter. And for an inverter, we know that the NAND gate, we typically size the PMOS device 2 times larger than the NMOS, right? That's the minimum size inverter. Okay, I would like to size now this guy here in such a way that I get the same delay at the output. Right? Basically the same current drive as this one here. What do I have to do? Well, these are parallel transistors. That doesn't matter. I can keep them the same size. Right? No problem. Because there's no serious connection. But here, in order to get the same resistance as this case, the same current drive, I have to double my transistors. Okay? So what's the input capacitance I see here? The total incapacitance of an inverter is what? It's 2 times the PMOS plus 1 NMOS. Let's say the input capacitance here is 3. What is the input capacitance of input A here? 2 plus 2 is 4. So to get the same current, I have to actually have an input capacity here which is 4, while for the inverter I have only 3. So the logical effort of the NAND gate is 4 over 3. That's the amount the NAND gate has to work harder than the inverter to basically work. So let's do the same thing for the NOR gate. Same game. Now those guys can stay minimum size, right? Because they're parallel transistors. Pulling down is easy. However, pulling up is hard. Because now I have serious transistors. When I want to get the same resistance in the pull-up path, and remember, I always take the worst case. If I look at the pull-up and the pull-down, I'm always going to consider which one is the worst case. Because that's the one I'm concerned about. That's the critical one. So in this case, in order to get the same resistance as the inverter, I have to double the sizes of the PMOSs here. So I haven't done that. What's now the logical effort? Any idea? It's pretty easy to compute, right? 5 over 3. So this is an interesting result. Actually, what it says already is that if you're really concerned about performance, actually you're going to be better off with NAND gates than NOR gates in static CMOS, right? And that's kind of easy to understand, right? If you have something hard to do, you would like to use the best devices you have, which are the NMOS devices. Because the PMOS are already slow to start with, and you make them work hard by putting a lot of them in series, you really need a lot of big areas to do so. So PMOS are hard, basically are not very good. So the NAND gate is the one where the burden is put on the NMOS devices. And that's why the logical effort is better for a NAND gate than for a NOR gate. So that's something to remember. This is a question I occasionally ask on midterms. What's the better one for if you do this logic style, NAND gates, NOR gates? Remember, in CMOS, NAND gates is the better choice. Okay, so that's, and by the way, the results were on the next slide, so that's why it was not hard to compute it. So here's the total picture now. Suppose I put an axis here. Remember what I did before for the inverter? It says, okay, the delay of a gate is a linear function of the fan-in, and this is TP, but let's now call it the normalized delay. For an inverter, we get a normalized delay of 1, T invert, and then we can see that the propagation delay is going to go up linearly with f. Right? That's the inverter. Now for an AND gate, we will see the same thing. We get the same expression, but now you see that the intrinsic delay has gone up. What factor? By this factor P. Right? This is the P factor that says that a NAND gate, even without a load, is going to be slower than an inverter. And then you have still a linear dependency, but this linear dependency is now going to be P plus LE times F. So for an inverter here, LE is equal to 1, P is equal to 1, so the delay is going to be equal 1 plus F. Right? If you normalize it to T invert. For the NAND gate, LE is going to be what? We have just derived it, is going to be equal to 4 over 3. P is equal to, let me just give you the first shot at it. If I look at how much slower intrinsically a NAND gate, 2-input NAND is going to be compared to an inverter, good bet is about a factor 2 approximately. So you can actually compute that, you can simulate that, it's not that hard to do. So P for a NAND gate is going to be about double than what you would get for an inverter. So my delay here is going to be 2 plus 4/3 of F. Okay? So we see that we don't only change the origin, 0 fan out case, that's the P factor, but we also change the slope of the delay. Okay? And that's true for NOR gates, NAND gates, and so on and so forth. Is this completely correct? Yeah, kind of. It's not completely, but it's a good approximation. And again, it makes our life simple. Because now I have this delay expression of a single gate. I can start putting down the expression for a chain of gates and trying to optimize it. Question?
What exactly does it mean when we talk about the fan-out of a complex gate like a NAND gate? We mean another NAND gate on the output that's twice as big or 4 times as big or what?
The fan-out F is defined exactly as we did before. I have, let's say, a NAND gate which goes to somewhere, and I have an input capacitance. That's the input, let's say, input 1, input 2, let's say. I look here as what's the total capacitance that this is hanging off here. And I look at the capacitance here. This is for part 1, and I say the ratio between those two, that's the fan-out. It's a ratio of capacitances. Okay? Now, input 2 can have a different ratio. You have to be aware of that my computation here is going to be dependent upon the input I pick. And very often it's symmetrical, but it might not always be. So you have to be a little bit careful about that. But it's just a ratio of capacitance. What do I see coming in? What's hanging off on the other side? Okay? That's what electrical fan-out is all about. It's an impedance transformation. Okay, one capacitor here, one capacitor there. Okay? All right, so I showed that. Some animation on it. I gave you the results. So, there we are. This 2 gamma. I think that the way these slides here do it is I don't perfectly like. I like to throw the gamma in the other direction. It makes life easier. But it doesn't make that much. Doesn't make any difference whatsoever. So this just repeats this whole thing here. Intrinsic delay plus the effective fan-out impact. Right? And it's the linear dependency. Okay. Now, I'm going to throw one little caveat in here. I'm going to forget about this thing for a little bit. But I just, obviously, so far we have looked at chains of gates. You know that in a logic network, obviously, you're not only going to have chains. I might have what's called branching. Right? For instance, one inverter can drive 2 inverters, and these inverters can drive 4 inverters, and this one can drive 7 inverters, and so on. So it's a tree network. And you have to take that into account. So we call this a branching effort. A branching effort of a given node is, let's say that this is my critical path, the ones I'm concerned about. I want to know the delay from here to here. The branching is, you took at the total capacitance on this node, okay? That's what we call the total capacitance, and we divide it by the capacitance which is sitting on the critical path itself. So let's say here, you have 2 capacitors, right? Let's assume they're the same. the total capacitance at node X here is going to be what? 2C. Right? So 2C. But only one of those capacitors is sitting on my critical path. So that's the on capacitance. See here. So you see that you have a branching factor of 2 in this particular case. If I would make this thing here 2C, and this one C, let's say I make them bigger or something like that, then the total here is 3C over C. That's my branching factor. Just remember this definition. I'm going to forget about it for a bit. We're going to come back to that later. Okay. Now, once I have this equation, I can do the thing as I did before. You have a long path. What's the delay of this path? Well, the delay of this path is going to be the sum of the delay of all individual components. Right? For every gate, we have Pi times LEI, the logical effort of that gate, times the fan-out of that particular gate. Some definitions now. I think it's important to kind of remember those things. Suppose I have a given path. Remember, a path is something that basically goes to the graph from the input to the output. So there's one path I'm worried about. That's my critical path. For the critical path, we can define the total path electrical effort. Like we did before. I have an input capacitance, and at the end I have a load capacitance, and I divide the two by each other. That's the effort that the whole network has to do. You have a little input here, big capacitor out there. What's the ratio between those two? So we call this the path electrical effort. Okay? Similarly now, on that single path, we not only have incapacitance, but we also have a variety of gates. There might be NAND gates, NOR gates, inverters, complex thingies, XORs, and so on and so forth. So we call the path logical effort just a product of all the logical efforts of the gates on that path. Okay? The effective fan-out of a particular gate, just for the heck of it, the effective fan-out is a product of the electrical fan-out times the logical effort. So we call this EFI. So you can say that the delay is PI plus EFI. Just making your life a little bit easier. Now I'm going to define one more, a couple of other interesting things, equations. The branching effort. If I now take my path, I just go to the critical path, and every point in that path we have defined the branching effort, right? The branching factor. So this one branches in 4, this one branches in 7. So you can imagine that if I look at this whole network and I drive it out, all those gates obviously have to drive all those branches. They have to work not only on the critical branch, but all the other branches. So it's important to know that how much of this whole thing is going to be going to the critical path. So you get that by just multiplying all the branching factors for every stage. Like first stage has a branching factor of 2, second stage has a factor of 7. You just multiply it out. That gives you an idea of how much on-path capacitance I have to drive versus the total capacitance I have to drive. Okay? That's the branching effort. Now, the path effort. That's another one. It's a couple of definitions, but you will see it's going to get clear with some examples in a minute. The path effort, PE, is like we have the effort, is the product of the logical efforts on the path times the branching factor times the electrical fan-out. You can see it, right? So you have a path. So okay, you have my electrical effort times the logical efforts. That's kind of how hard I have to work for the path, and then you multiply this with the branching factor to figure out what the total path effort is. Okay? And this thing we already know, the path delay D is the sum over all elements of Pi. Well, actually they have double sum in here. I don't have to put the brackets in here. It's Pi, the sum of the Pi's, plus the sum of the electrical efforts. A lot of words. Seems a little bit confusing, but don't worry too much about it. Let's do a little example. Well, before I go to an example, again now, if you look at this equation, okay, that's my path delay, Pi plus the sum of the different electrical efforts, or effective fan-out, sorry. If I look at the minimization, like we did before, we try to minimize the overall delay of our network. if we would take differential equations with respect to the sizes of all the different elements, what would you find is that the circuit, the sizing that's going to minimize your overall delay is the one that's going to equally divide the effort over each stage. Right? You make sure that every stage in your network works as hard as the other ones. Because every time there's one that kind of would do more work than the other one, you can see that you're going to be in a local optimum, that you actually can do better by taking some of the work away from it and give it to somebody else. That's exactly what we saw for the inverter chain, and we showed that by taking the derivatives. You will see exactly the same thing here. If you take the derivative, you see the best thing to do is divide and conquer. Everybody does the same amount of work. Nobody more, nobody less. So every stage does the same effort. So the path effort, PE, remember that? That's the definition of this branching times the electrical fan-out factors times the logical effort. So we're going to take that path effort and say every stage does the same thing. So the effort for every stage, EF, is going to be the nth root out of PE. Okay? So once I know PE, I take the nth root and say, okay, every stage has to go, and as a result of that, I have the effective fan-outs of each of the stages. And once I've known that, I can start optimizing exactly the size of my transistor to do so. Just like we did before. Okay? But remember, there's some little extra games coming in here because, you know, some of those things are NAND gates. Some of them things you will see that the sizing will be determined if something has a lot of logical effort to do or something that basically has an easy thing in life, like an inverter. It's easy to drive things. NAND gates and NOR gates have to do a harder job. And the optimal number of stages, again, can be defined in the same way as before. It's the same thing. You can basically take the derivative of those factors. You define it out. You say, here's my overall load. You can say that it's given the best effective fan-out is given by PE over the 1 over N, which is still 3.6 with gamma equal to 1. Hasn't changed. It's the same equation you're getting. We just have other factors in here. It's not anymore purely electrical fan-out, but actually is my effort of my stage, which is the product of the logical effort and the electrical fan-out. Okay? That has to basically be equal to 4. Okay, let's do, I think next one is an example. Well, we're almost there. Before we can go to example, I just want to summarize a little bit of some of the parameters before we go in there, because that allows us now to do some example. If you look at the logical effort, an inverter, per definition, equal to 1. Right? We derived the value of an AND gate and NOR gate, 4 over 3, 5 over 3. You can see that this is easily extendable to more input fan-in, or larger fan-ins, 5 over 3. For an AND gate, the logical effort is going to be n plus 2 over 3. Okay? For an NOR gate, it's 5 over 3, 7 over 3. See, guys, it actually goes up a lot faster with n. Remember, again, because of the series connection of PMOS devices. XORs is a little bit more complex because XORs have, if you put an XOR in a CMOS implementation, things are, let's say I want to do AB plus AB bar. That's really what a XOR would be. You get something like this. And so this is A, B, A bar, B bar. And you get actually a fairly equivalent network at the other side. If you derive it, you can actually find that XORs actually go up quite substantially with the number of fan-in. 4 for a 2-input fan-in. You have basically do an XOR with 3 inputs. It goes up to 12. So logical effort of XORs, large XORs goes up actually quite rapidly. Okay, well, let's not go too deep into that for the time being. Okay, let me just skip over that a little bit just for the sake of things. So, well, no, let's do it anyhow. because I'm going to have to do it. Now, I have to do some other sizing conventions because it's always hard to figure out what do you compare to what. What does sizing mean? Okay? What does a gate of size 2 mean? It all depends on what you compare it to, right? So for an inverter, it's very clear. All right, if I make an inverter 2 times larger, I'm going to get C invert is going to be 2 times larger, and R invert is going to be a half. Right? I make my resistors double. Resistors basically, I size up the size of the resistors. So as a result of that, my total resistance basically comes to a half. My capacitance goes up with a factor of 2. Right? For a gate, however, there's 2 options. If I make a size gate of 2, on one side you double the capacitance, right? Or I reduce the resistance. Okay? So what we're going to do for our definition here, I'm going to talk about this. This is what we this is just a convention. My convention is that a gate of size 2 has the same. It's basically a gate that has the same resistance as the inverter, but basically double input capacitance. So we're going to compare every time we say a gate is n times larger than another one, then or a gate has size 10. What we mean by that is it has a driving resistance, which is equal like an inverter, but it has a 10 times larger capacitance. Okay? That's just the definition we're going to use here, and it's going to make life a little bit more convenient. Okay, this is a little repetition. We've done that. We know the logical effort of this guy here. Yeah, if you have a given gate with certain fixed sizing, let's say you have this gate here. What's the inverter with the same resistance? Right? That's really what you worry about. Well, in this case, obviously, 2 times in sequence, that would basically be 8. Let me just check here. Trying to get the answer on this thing here. So you find, let's say, this is a gate with a particular size. What is an inverter that basically has the same resistance? And then I can determine the capacitance, and I know what the ratio between those different factors would be. So in this case, if I look at it, the inverter with the same resistance would be something that has a factor 8 here, and in the worst case would be 4 here. And that's basically saying, well, gee, this is a device which has gate 8 or size 8. Okay, so let's start with an example. I want to design this sequence of gates. I have a path that's given. I know that my input capacitance is 1. My output capacitance is 5. Means that the output capacitance is 5 input gate capacitance of an inverter, right? That's what I know. And the other only factors I know is that I have a NAND gate, 3-input NAND gate of size A, a 2-input NOR gate of size B, and an inverter of size C. So now the question that I have to ask myself is, what's the size A? How should I basically determine what's the values of A, B, and C that are going to minimize my propagation delay, right? That's the question I'm asking. Okay. So what I'm going to just do now is use logical effort to find out exactly what this thing should be. So what we have to do first is determine the logical efforts. Okay? Logical effort of an inverter, that's an easy one. It's 1. Okay? Logical effort of a 3-input NAND gate. If I go back to my previous equations, it's, I believe, what was it? It was n plus 2 divided by 3. Right? It's 3 plus 2 divided by 3, 5/3. The NOR gates is 2n plus 1, I believe, divided by 3. So it's 2 plus 2 is 4, plus 1 is 5, 5/3. So actually, those things have exactly the same logical effort. Because the NAND gate, obviously, is a 3-input NAND gate. This is a 2-input NAND gate. This inverter is logical effort of 1. So that's quite nice. We have that. So it's easy for me now to right away compute the total path logical effort. It's the product of all those factors. 1 times 5/3 times 5/3 times 1, that's 25 over 3. So the path effort is 25 over 9. Correct? It's just multiplying all the logical efforts. Okay? So now what's the product of, what's the total electrical fan out? We know that too. Any idea? The first factor, electrical fan out of this network is what? And no peaking. Electric fan out, remember what the definition is? Ratio of load capacitance over input capacitance. Very simple, is what? 5. Yes. So we have 5. Sorry, I am wrong here. This should be here, 25 over 9. So what's now the total path effort? The path effort is the product of the effective fan outs per stage, is the product of the electrical fan out of the path times the logical effort of the path. So it's 25 times 5 is 125 divided by 9. Okay? Now, remember, what we're going to do is equalize or equally distribute that effort over every stage. Okay? So the effective fan out per stage should be what? Is the 4th root out of 125 over 9. I have no clue what that is. It's probably going to be on the next slide. What's the number? 4.9. Let me just peek myself. 1.93. Right? So 1.93 is the effort. So you can see that every stage is going to do an effort which is approximately equal. But remember, it's not going to be the same as before, where we just say, okay, 1.93, they all going to have the same thing. It depends really on the logical effort. How we're going to size now is going to be depending upon the efforts per stage. And that's really what you have to do the effort for here. You can see now that if every one, the EF per stage is 1.93. For an inverter, that's easy, right? For the inverter, you have 1. That's the first stage is stage 1. So let's look at the size of is gradually work out from here, from the beginning. And we know that this thing has an EF of 1.93. So we're going to have to define what sizes of transistors will basically give me exactly that particular number. Right? So I know the electrical fan out of the structure. I know what the load is. So we have F of stage A times the logical effort of stage A is 1.93. We know that. So out of this, we can compute, we know the logical effort of this stage is 5/3. Okay? So this is 5/3. Out of this now I can say, okay, this is the fan out that this stage is going to be able to provide. Okay? And by defining the fan out, I know the input capacitance, I basically have the load of the other capacitor. What I can start working out step by step here is a set of equations that relate A, B, and C. Okay? So 5 over C, C is an inverter. We know that the total effort is going to be 1 over 9.3. So C is the size factor, that's the input capacitance. We know that the output capacitance is 5C, that's the electrical effort. The logical effort is 1, so 5 over C is 1.93. So you work backwards here. Okay? The second stage is a little bit harder, this B stage, because we have the logical effort is 5/3. The electrical effort is C over B, the size factors. That's also equal to 1.93. And for stage A, 5/3 over B over A is also 1.93. So I start at the back, and I gradually work to the front. Okay? So here I can find what C is going to be like. C should be equal to 5 divided by 1.93. I find this size factor here. Once I have C, I can find B. Once I found B, I can find A. And I'm done. I basically found out the relative size. Remember the relative size of the one that basically has the same resistance, and we compare the capacitance compared. That's really what our size factor is. Okay? So, very simple technique. Think about what I did. I computed the path effort. I computed by looking at the logical effort of a complete path, the electrical fan out of the complete path, multiply them all out, take the end root, find out what the optimal logical, or basically the logical stage effort is for every stage, which is 1.93. And then working from the back, I say, well, if I know my stage effort, the effective fan-out is 1.93, that's equal to the logical effort times the fan-out, and the fan-out is the ratio of the input capacitance and the output capacitance. So in this case, electrical fan-out is 5 over C, where C is the size of this device. Here it's C over B. This is B over A. Multiply with the logical effort, put all the things, and solve them. Okay? So out of this, bingo, come the optimal sizes of my transistors. Very interesting exercise. And you can do this for a lot of networks. Now remember, my question I asked way back, said, hey, remember this? Which one is better? I have an 8-input AND gate that I want to implement. Should I do this as 2 gates, an 8-input NAND gate followed by an inverter, or 2 4-input NAND gates with a NOR gate behind it, or 4 2-input NAND gates, and then so on and so forth. So let's do the simple exercise again. And I'm going to give you now the absolute final answer, at least for a particular technology and topology. So the logical efforts we can compute, right? The logical efforts of this thing is an 8-input NAND gate. 8 plus 2 divided by 3 is 10 over 3. This thing's here, 4 is 2 plus 2 divided by 3. Wait a second here. NOR gate is 5 over 3. I'm just still thinking about this was n plus 1. It was n plus 2 over 3, right? So you have 4 plus 2. Yep, that's correct. It's 6 over 3. So we get a logical effort of 2. Here, 4/3, so on and so forth. So we can define the logical effort of every one of those things. We can find the fan-out, obviously, is the same. You want to make sure that this has a minimum input capacitance here. You have a certain load capacitance here. So the product of the logical efforts is computable. That's 10/3. It's 10 times third over 1. This is 2 times is also 10/3. This is 80 over 27. Now, 80 over 27. Let's think about which one is the largest one. It's amazing that its 2 first networks actually have exactly the same logical effort. So from a delay perspective, we might not see that much different, at least from a load driving capability. This one has 80 times over 27. That's, let me just divide this by 9. Actually, this is smaller. Right? If you just divide this by 9, 80 by 9 is approximately 9. So it's probably 9/3, 8/3 approximately. So this has smaller logical effort than the previous 2 networks. That means in terms of driving a big capacitor, I'm going to be better off with the last structure. It's going to be the one that's going to be, for me, giving me the better performance. Now, obviously, from a delay perspective, it's not. We have the fan-out, remember, the overall fan-out factor. That's the same in all cases. The electrical fan-out. Logical effort is smallest in the 3rd case. We also have to look, obviously, at the parasitic delay. This has a parasitic delay, assuming that for a NAND gate, the parasitic delay is proportional to the size of the gate. This is 1, this is 8, this is 9. This is 6, this is 7. So you can see here what's happening is by putting more and more gates in sequence, you get a certain optimum, right, for in terms of this thing. The more stage, suddenly the number of stages is going to start to dominate. But if you put the 2 together for a given factor, so the delay is going to be 7 plus logical effort times the fan-out, you can see that very often, most often, this is going to be the best solution. It's going to be the fastest topologic network. Which is obviously not, that's not obvious, right? If you look at it, it's a, boy, this is so much more complex than the other one. This should be faster, like just one gate. But it's not. Because this gate has a hell of a time driving anything. And has this big logical effort type of thing. So that's kind of an idea of what you can do with this. Actually, now I have the tools in my hand to objectively compare different results with each other. And this is something that you're going to apply for sure in the project. If you're going to do sizing and things like that, this is the kind of tools we're going to start playing around with for you to take a first shot I don't want to see, if I say, here's this particular gate structure and things like that, size it to me in such a way that's optimal, I don't want to see 500 spice runs. Now, you could get the right answer, but it's going to take you a little bit. So, as I said, use your brains first and use spice after. Okay? So, what we're going to do next lecture is I need to do one more expansion of this because so far I've only done chains. I haven't talked a little bit about the effect of branching. Remember I had a branching factor? I'll show you some examples where I start playing around with branching factors. And then you're there. You have everything. Okay? Good. So I'll see you again next Wednesday. Sorry? No. The hardware lab is going to be somewhat later into the future. So no lab.